Let's talk about determinants in this video. Recall that a 1x1 matrix, say A, with entry little a, which is the same as a real number A, is invertible if and only if little a is non-zero. Also, a 2x2 matrix A with entries A, B, C, D is invertible if and only if A times D minus B times C is non-zero. In other words, we can use the numbers A and AD minus BC to determine whether a 1x1 matrix and a 2x2 matrix is invertible respectively. Let's see if we can extend this idea to 3x3 matrices. That is, we want to find an expression which involves the entries of the 3x3 matrix to determine whether that matrix is invertible or not. Let's formally define this idea. This number, which we can use to determine whether a matrix is invertible, is called the determinant of the matrix. To denote the determinant of a matrix, we write det in front of the name of the matrix, or put two vertical lines around the entries of the matrix without the parentheses. So, we define the determinant of a 1x1 matrix A with entry little a as just little a, and the determinant of a 2x2 matrix A with entries A, B, C, D as AD minus BC. Let's also define the determinant of a 3x3 matrix, say A, with entries A, B, C, D, E, F, and G, H, I, to be the following expression: AEI plus BFG plus CDH minus CEG minus AFH minus BDI. It is hard to see why this number defined for the matrix has anything to do with its invertibility, but we will slowly develop concepts and properties around this number, and finally show that the matrix is invertible if and only if this number is non-zero. First, let's see how we can remember this long expression. One way that we can do so is to first write the entries of the matrix, and write the first and the second column again on the right. Observe that the first term, namely AEI, is the product of the main diagonal entries of this 3x5 matrix. Also, the second term, BFG, is the product of the diagonal entries on the right of the main diagonal. And similarly, CDH is the product of the diagonal entries on the right of BFG. This gives the first three terms, which are all positive. The other three terms, which are all negative, are the products of three other diagonals which go in the other direction. Even though this is a good place to start, it is still not a very easy way to remember. Also, this is hard to generalize to determinants of matrices of larger sizes. In fact, there is another way to remember the determinants of matrices, which can be easily generalized to matrices of larger sizes. For this, we introduce two definitions. Let A be a square matrix. The ij minor of A, denoted by A subscript ij, is the square matrix obtained from A by removing row I and column j. Second, the ij cofactor, denoted by Cij of A, is the scalar -1 to the power I plus j times the determinant of the ij minor of A. Note that the signs of the cofactors, namely -1 to the I plus j, can be remembered using the following diagram. The top left entry is always a plus, and the signs alternate between plus and minus as we move away from this entry. Let's see some simple examples of these two definitions. Let A be the matrix 1, 2, 3, 4, 5, 6, and 5, 0, 8. Then, the 1, 1 minor of A is obtained by deleting the first row and the first column, so we are left with the matrix 5, 6, 0, 8. Similarly, the 1, 3 minor of A is obtained by deleting its first row and third column, so we get 4, 5, 5, 0. For the cofactors, suppose we want to find the 3, 1 cofactor of A. To determine the sign, let's draw this diagram for a 3x3 matrix, Since the 3, 1 entry is the bottom left entry, we know that the sign is positive. We also know that the 3, 1 minor of A is the matrix 2, 3, 5, 6. So the cofactor is the determinant of this matrix, which is 12 minus 15, which is negative 3. Let's look at another cofactor, say 2, 3 cofactor of A. From the diagram, we know that the sign is negative, and the minor is 1, 2, 5, 0. So the cofactor is negative of 0 minus 10, which is 10. To see why these two definitions are useful, we look at the following proposition. Let A be a 3 by 3 matrix with entries aij. Then, the determinant of A can be written in the following ways. The first one is A11 times the 1, 1 cofactor of A, plus A12 times the 1, 2 cofactor of A, plus A13 times the 1, 3 cofactor of A. This is called the expansion of the determinant along the first row. This is because the entries and the cofactors involved in this expression are from the first row. Similarly, we have expressions for the determinant which are expanded along the second row, the third row, the first column, the second column, and the third column. We can show that all these expressions are equal to the determinant of A, so we are free to find the determinant of the matrix by expanding along any row or column as we like. To prove this, we just have to use the definition of the cofactors and rewrite the expression so that we obtain the definition of the determinant. We show the expansion along the first row, and the rest are similar. So we start with the expression A11 times the 1, 1 cofactor of A plus A12 times the 1, 2 cofactor of A plus A13 times the 1, 3 cofactor of A. Applying the definitions of the cofactors, this is equal to A11 times the determinant of A22, A23, A32, and A33 minus A12 times the determinant of A21, A23, A31, A33 plus A13 times the determinant of A21, A22, A31, and A32. Using the definition of determinants, this is equal to A11 times bracket A22, A33 minus A23, A32 minus A12 times bracket A21 times A33 minus A23 times A31 plus A13 times bracket A21, A32 minus A22, A31. By removing the brackets and reordering, this is equal to A11, A22, A33 plus A12, A23, A31 plus A13, A21, A32 minus A13, A22, A31 minus A11, A23, A32 minus A12, A21, A33. We can check that this is exactly equal to the definition of the determinant, and so the proof is complete. Let's end this video by giving an example of computing the determinant of a 3 by 3 matrix. Let's consider A, which has entries 1, 4, 5, negative 2, 5, 0, 9, 6, negative 8. First, we observe that the 2, 3 entry is 0, so if we expand along the second row or the third column, one of the terms will vanish, so we will only get 2 terms instead of 3. To illustrate that both expansions will work, let's do both expansions and show that they are the same. If we expand along the second row, the determinant of A is equal to negative of negative 2 times the determinant of 4, 5, 6, negative 8 plus 5 times the determinant of 1, 5, 9, negative 8 minus 0 times 1, 4, 9, 6. So the third term vanishes. We get 2 times bracket negative 32 minus 30 plus 5 times bracket negative 8 minus 45, and the answer is negative 389. If we expand along the third column, the determinant is 5 times the determinant of -2, 5, 9, and 6, minus 0 times the determinant 1, 4, 9, 6, plus -8 times the determinant of 1, 4, -2, and 5. So this time the second term vanishes. We have 5 times bracket -12 minus 45 minus 8 times 5 plus 8. So we get -389 again. So the answers are indeed the same.